Alright, so today we'll start by going through the collection classes in the Onion, and if we have time we'll also go through the console server. So a little bit first about the philosophy of our collection classes. We have no STL classes in the Onion because we want full control of what the collection classes do. We want to be able to see the performance, see the memory use, and so on. So that's part of the reason why we're not using STL. But an even bigger reason is, as we saw in the last presentation, we have our own allocator system. So our classes, our collection classes need to be aware of that allocation system. And the STL doesn't allow you to have an object as an allocator. You have to like template on the allocator, and it becomes super messy and doesn't work at all with our allocation system. So we don't use any STL classes. We use STL algorithms though, and a lot of them are kind of useful because they work directly on pointers, and so they don't need anything other than a buffer like find and sort and the heap push and heap pop algorithms we use. And those have like well-known performance, so there's no big issue in using them. Overall, we have kind of a minimalistic philosophy when it comes to the collection classes. We have very limited number of collection classes. We focus on the few classes that we actually need and don't try to have a huge amount of collection classes, because that just tends to create confusion and people picking the wrong class. And actually you don't need that much. An array and a hash map is pretty much all you need. You can sort the array to do binary search, and you can use the hash map when you need order one lookups. So that's pretty much all we need. We have some other stuff too, and some of it is legacy that we could get rid of, but that's most of what we have. We also try not to abstract too much over our collection classes so that you know what the collection class is. It's okay to know, for example, that the string is an array of characters. We don't pretend that it's something. We don't try to hide that implementation too much. There's no point in that, because we never want to change that basically anyway. And knowing what it actually is means that you know the performance of stuff, you know what to expect from it. So I think it's useful to not hide too much of what stuff actually are, and it makes things simpler to reason about. So the first classes that are important to know about is array and vector. So array is a pretty simple class. Basically, you can, if we skip all these functions that are kind of modeled on the STL interface, an array is basically just a pointer to an array of data items. There's a size that says how many items there are. There's a capacity that says how many items we've allocated, so we can, how many items we have room for before we need more. And then there's a reference to our allocator that we use to get more memory when we need more memory in the array. So it's pretty simple. And it grows exponentially. So whenever it grows, it like doubles in size. And the nice thing about that is that if we do that, then the cost for growing the array becomes linear when it's amortized. So the cost for, so each time you grow if you grew the array by a fixed size every time, then it would cost more and more eventually, because you would be copying more and more data as you copied it from the old memory location to the new one. So you would pay more and more for allocating 10 elements. But by allocating the double size of the array, that means that the cost of moving is proportional to the amount of new elements that you create, which means that if you average out over the entire creation, the cost becomes linear. So that's nice. So we have two of these classes, array and vector, which are kind of similar. They both have all these fields, and they both represent an array of items. And the difference between them is that the array class uses memcopy when it needs to copy the elements, while as the vector class uses proper constructors, so proper C++ constructors. And the reason we have two classes is that array can be a lot faster. For example, if you just need array of characters, depending on what kind of optimizations your compiler makes and whether you run in debug mode and so on, so depends on what actually happens when it gets compiled. But the vector class can be like a lot slower if it actually calls a function for every object, for every character, and tries to construct that character in its memory slot. So the array class is a lot faster when you have plain old data, just raw structs or integers and chars. But we need this vector class if we need the constructors to be called. So if we have objects that need to be initialized, that are like proper C++ classes that need a constructor, then we use the vector class. So generally you should use the array for everything that's just simple data, and use the vector when you're dealing with objects. So an important special case is when we have an object that needs an allocator. So that's for example our vector classes. So the vector needs an allocator to allocate its memory. You can't just create the vector without passing in an allocator. So this happens, for example, if we have a vector of vectors. Then this outer vector, when it creates these inner vectors, it needs to know that this inner vector, this template type that this outer vector is storing, it needs to construct these objects by passing in an allocator. So somehow this vector class needs to know what kind of object it's storing, if it's simple objects that don't need an allocator, or if it's these more complicated objects, so it needs to pass an allocator to them on construction. And this is all done with macro and template magic. So the way it works is that you put a special macro, which we call allocator aware, and you put that in the definition of a type. And if you put that definition in, the vector class can check for that using some template magic. You can go in and look at the file if you're interested exactly how that template magic works. It's like all template magic, it creates some struct and then you can sort of switch on that struct in the templating code. But anyway, through that template magic, the vector class will know how to call the right constructor. So this is something you need to be aware of when you define your own objects and want to put them in vectors or in array, that if you're defining an object that needs an allocator, you need this macro to put in there. But you'll get an error if you don't put it there, because then the vector will try to create it using the default constructor without any arguments, and since that constructor doesn't exist, you will get an error. So, but it's useful to know what you need to do if you get that error. So mixing allocators, this can be something you wonder about. What happens if you have collections and you sort of mix allocators between them? So in this case, I have a function that takes, it has some vector that it takes in, and then it allocates its own vector here, and then it pushes that vector on the other vector. But this vector has a different allocator. This one uses just a temporary allocator with memory that will be released when this function goes out of scope. While this one has some other allocator that we don't really know about, since it's passed into us. It might be whatever allocator. So you might wonder what happens here. Do we create a problem because we could push a vector that has this temporary memory, and now the temporary memory goes out of scope? But this is actually safe. And in general, all these kind of mixing operations between collections that use different allocators is safe. So what happens here is that when we do this pushback here, we will create a new vector int in VV here using its allocator, so whatever allocator it had when passed in. And then an assignment operator will be called to assign this single v into that vector we just created in VV here. And this assignment operator will copy all the data. So the vector we created here will keep its allocator. And the data will just be copying. So in short, mixing allocators like this is safe. It works as expected, and there's really no way of messing up here. But in general, we tend to want to avoid this pattern because when you have these like vectors of vectors, there's a lot of copying that can happen behind the scene that you don't really see what's going on here, that in fact all of these elements are being copied here. So it can be expensive, more expensive than you expect. So we tend to avoid this pattern, but it is safe to mix allocators this way. So strings, we don't really have a string class in the engine, which is kind of a controversial choice. Most collection systems have some kind of string class, but we don't, because string classes are stupid. And the reason they're stupid is that we have two kinds of strings in the engine, which have very different use. We have either static strings, which have a value and they don't really change throughout the running of the code. And then we have dynamic strings that can sort of grow and shrink, and the content can change and so on. And these strings are have very different behavior. With a static string, we don't need to, it can reside in the same memory space the whole time. It can be part of a bigger object, a bigger memory blob. It doesn't matter at all. Whereas, well, these dynamic strings need to be able to shrink and grow and do all kinds of things. And in a game engine, we typically have a ton of these static strings that don't need to change, and we have very few of these dynamic strings. So if you were to use the same string class for both of these strings, which is what you end up doing usually if you have a string class in your system, then we would waste all of that performance for these static strings, because we would have to give them the dynamic capability, or we would have to have strange switches in the string classes, like is this a dynamic string or is this a static string, which also is kind of stupid, because it's two different things. We should just represent them as two different things. So that's what we do in the engine. For static strings, we just use a sharp pointer, like the regular C. That works fine for those strings. And for the dynamic strings, we just use an array of characters, because that's basically what a string is. It's an array of characters. These strings are also always UTF-8. It's the only sane encoding for strings. So whenever you see a string in the engine, it's always UTF-8. And if we need some other encoding for calling Windows function, for instance, we convert in and out at the point where we call that function. But internally, we always use UTF-8. So in the string class, we have some helper classes here, but they don't really do anything. We have a helper class constring, which just wraps a sharp pointer and makes it so that we can do equality on it. So, which makes for a little bit nicer code. You could argue whether you should have this function or just call strcomp all the time. And we have a dynamic string class, but that class for our dynamic strings, but that class is just it just wraps a character buffer, and we don't try to hide that fact that it's just an array of characters. You can access that array if you need, because sometimes you want to maybe reserve more memory or do something special with this buffer. And if we sort of hidden the implementation, you wouldn't be able to do that, or we would have to create a lot of functions in the interface of this class to enable all that. But that's kind of silly, because we know that the string is an array of character. We will never make it something other than an array of character. If we needed something that wasn't an array of character, we would create a new class to represent that. We wouldn't sort of morph this class into something else. So apart from this, there's a lot of helper functions here, and those for things like finding characters, checking for white space, and those are all implemented outside the class itself, which we like, because then we can extend this. It means we don't have all the string functions stored in this header in the string class. We can add new string manipulating functions wherever we want them in the project, which is what we want. Then there's our hash representation. So we have two of these: hash map, which maps from one type to another type, and we have hash set, which only contains keys. So there are no values stored under these keys. We just keep track of which keys are in the set or not. And the main thing that we want from the hash map is that we have order 1 lookup. So given a key, we can, in one operation, in constant time, we can find the corresponding value. We use open hashing, which means that instead of rehashing on a collision, we have a linked list in each hash bucket that we follow to find elements that have colliding keys. But we don't store the linked list by allocating usual linked list elements, by allocating each element one at a time, because that's very, very inefficient given the way memory behaves today, where cache misses are really expensive. So instead, we store everything is stored, all the data for the hash is stored in one big array. And in the first part of the array, we have the regular sort of hash item buckets. So when you hash the key, it will hit one of these buckets. But then at the end of this, after all these regular items, we have a collision spill area that we call it. And that's where we call, if we have a collision when we store something in one of these buckets, we will link to an element in the spill area. So we'll have a linked list, but all the nodes in the linked list will be in the spill area. So we hash, we hit one of the buckets here. If the key doesn't match, we follow the linked list into the spill area, and there might be multiple links here, so we follow them through the spill area until we found the item or the end of the spill area. So this is just an array of items, like regular buckets, and then collision spill area. And all the items are stored as, we first store the key value of the hash, whatever the hash uses as a key, so we can compare the keys to see if they match. Then we have the value stored, or in the case of the hash set, there is no value stored, there's just the key. But if it's a hash map, we store the value type. And then we have a marker field. So the marker field is used to indicate if a slot is empty, for instance, because we don't know the space of the keys, because the keys can be any type, so we can't use like a special key value to mean that this cell is empty. So we have to add extra storage for that. So we use that to mark when a slot is empty, but we also use it for this linked list. So this marker can either be a value that says that this slot here is empty, or it can be a link into this spill area so that we can follow and find all the keys attached to the same value. And we use murmur hash as our hash function. It's in this file, hash function.h. And eventually, when we deem that when this has filled up, either because the buckets are full or because we've filled the spill area, so we can't spill any more items there, we'll rehash the entire, we'll grow the entire hash map. Again, we'll grow it exponentially, like double in size every time, and we'll rehash all the items to put them back in the hash map again. Then we have a class called IDString. And the reason for the existence of these classes, there's two of them, IDString 64 and IDString 32. The reason for them is that most of the time when we deal with strings, we really only want to compare them by identity or do a lookup in a hash table based on them. So, for example, for resource names, we have some resource that we want to spawn. Then we typically just want to look up that resource in our list of resources. And since we just want to compare it or just use it as a lookup, we don't really need the full string. It's enough to just use a hash of this string. So the murmur hash of the string. And this brings us several nice things. For once, we get faster comparison, because instead of doing a string compare, we have to compare character by character. We can just compare the two hashes, so it's a single int64 operation. It's also less memory use. Instead of storing lots of strings in memory, we just store these numbers. But the kind of best advantage, even better than these two, I think, is that is that we can store the hash in a fixed size. So the hash of the string will always use 64 bits, whereas the string itself, it might be 20 characters long or 200 characters long, and so on. So if we try to store them in an array, we can't store strings directly in an array because sizes vary, so we have to store pointers, and then we have to follow the pointers to get to the real string. And since the strings grows and shrink, managing all that memory is kind of complicated. While as when we have fixed size, we can just store them in arrays, we can create a struct that has these string hashes in them, and so on. So it leads to much nicer structure of the code, which is really nice. So using a hash is really useful. And these IDString classes are basically just classes that wrap a hashed string. So there's not that much to them really. It's just, we have a class IDString64 here. It takes a constructor, which is either the hash value or the string itself, and it will produce the hash. And yeah, it just stores this hash value. And we have a similar one for 32 bits. So depending on how big the string space is and how much memory you want to save, you could use either 64 bits, which reduces the chance of collision in the hashes, or 32 bits if you just have a few strings, like 10 or 20 strings or so, and you don't think a collision will be that likely. We don't really have a way of dealing with collisions in IDString, so if you're that unlucky that you run into a collision, it hasn't happened so far in the 7 years we've been working with the onion, but if you do it, you need to rename something. But the chance with 64, if you use 64 bits, you would have to need to create about 4 billion things before you start to expect a collision, so it's kind of unlikely. So printing ID strings. Now, there are situations where we would like to reverse our hashes, to take our hash and get from the hash back to a string. So some common situations are, for example, when you look at the value in the debugger, you're debugging something and you see there's something wrong with an object, and the object is called 3CA5, some weird hash. That's not super helpful. You would like to be able to get the string back so you can actually know what it is that's going wrong. The same thing applies to error messages. If there's some error in the data, we want to be able to print a useful error message. We want to be able, if a resource is missing, for example, we want to be able to print the name of that resource and not just this hash that doesn't really help the user. But if you look at the way things are implemented, we just have a hash and we have no way to reverse it. And we don't really want to use the memory to store all this string data. As I said, it's really nice to only have this hashed representation. So how do we deal with that? Well, the solution we have is that we have a file that's called StringStopText, which is generated during the compile time. So that file is actually stored in your data folder together with all your compiled resources. We will also generate this file. And this file contains all the unique hash strings that are encountered during compile time. So if you look at the implementation here, there's an IDString repository. This is only active during compile time. And when we create it, it will read in the StringStext file and read in all the strings in that file and keep them in memory. And whenever we hash a new file or hash a new string, we will check if we know about this string already, and if we don't know about it, we will add it to our list of strings in this StringStopText file, and we will save it out. So this file will actually have all the strings we've ever encountered. And the tools can use this to do a reverse lookup. So the tools will open this file, hash all the strings in the file, and then when you ask for what does this mean, the tool can look up all the strings it knows about and their hashes and check, well, do I know what this string means? And in that case, the tool can print it. So we have, there's in the console, in the external console, there is an ID lookup tool where you can enter these IDs and get the string back. So that's kind of useful when debugging. And the console will also automatically translate ID strings that are printed by the engine. So if the engine prints something that follows this pattern, it starts with hash ID bracket and then an ID, the editor will automatically take this, look it up in the string table, and convert it to a string and print the right string. So that's how you get a proper error message instead of this weird. When the engine prints it, the engine will actually print this thing, but in the console it will be converted to this thing. So if you're looking at the output not through our console, but looking at the output in the command line, for instance, you will just see these hashes, since the console is responsible for the translation. Now, an important note here is that we only do this during compile time. Store all the strings that we encounter. Because if we did it during runtime, it would be pretty expensive. That would sort of defeat the whole purpose of using hashes to begin with. So we only do this during compile time, which means that if this hash comes from a string that has only been seen at runtime, then we don't know, the editor won't know how to reverse it. So if it's a string that has been entered, for example, if Lua has created some string, concatenated it, and we hash that, then the editor doesn't know how to reverse it. So in that case, we actually have what we do is that we print the error message in our Lua API, because from Lua we will get the full string before we hash it, so we can print a full string message. But the important thing here to note is that there are some situations where you won't be able to reverse this hash, and you will only have this weird hashed value to work with, which is kind of annoying. So you could ask whether this optimization makes sense anymore. Now, when we started working on BitSquid, we were targeting PS3 and X360, which are platforms with very limited memory. So we had to be really careful about how much memory we use. But today, all the platforms we're running on have like pretty decent amounts of memory. And this string table isn't super huge. So you might question whether this optimization of not storing the string data, whether that makes sense. We could probably keep this string table, instead of having it just on disk in this StringStopText file, we could probably keep it loaded in memory. Note that we would still want to use hashes everywhere, because hashes, they have this nice comparison speed, and you also get this nice struct layout. So we definitely want to use hashes everywhere, but we could keep the string table in memory, so we could always do the reverse lookup from within the engine, and then we would never run into the situation that we have some weird string and we can't reverse it, so we don't know what the error is. So that's something to think about for the future. Final two classes I want to talk about is the option and error classes. These are classes that represent concepts similar to the algebraic types that you have in languages like ML or F#. So it's basically just types that we use for cleaner error handling. So the option type either represents a value or a nil. So that's useful when you have a function that can return something, or it might not be able to return something, like a find function, for instance. It's a bit cleaner to use this option wrapper rather than say, well, if we don't find something, we return -1 or some arbitrary value like that. By using an option class instead, you make it very clear that you are returning a non-value. And the error class is kind of similar. It returns it contains either value or an error message, which is in this case is just a sharp pointer. So if you have a function like this use example here, if you have a function that might fail, like any file system function can typically fail. So the size function, when you ask for the size of a file, it will actually return the size wrapped in this error handler, and then you can check, was there an error? And if there was, we'll print an error message, and otherwise we can sort of go on and working it. So by using this construct, we're sure that we'll never forget to check the error code, which we might otherwise. If we returned an integer error code, for instance, it's very easy to forget to check that, but this kind of forces you to check it. And if you don't check it and just use the value, there's an assert there that asserts that there was no error. So if we look at this code here, it's pretty simple. We just have we just store the value, and we store an error, which is null pointer if there is no error, and then we have functions to check what state we're in. So pretty simple. So that's it for the collection classes. Are there any questions on that? Okay, let's take like 3-minute break or something, and then we'll continue with the console server.